Now let us continue. If you ask me the definition for power electronics is a technology associated with efficient conversion and control of electric power by using power semiconductor devices. Because in analog electronics also we are using semiconductor devices. They are signal semiconductor devices. I am not talking about diodes, BJTs, MOSFET. I am talking about power diodes, power BJTs, power MOSFETs, and so on. So because we are using this for high power applications. So please remember, this is the definition for power electronics. If you ask me, at least from my opinion, I would say this is a technology associated with efficient conversion and control of electrical power by using power semiconductor devices. So what is the goal of power electronics? To control the flow of energy from source to load. To control the flow of energy from source to load. Okay, so it's important to understand the concept of power electronics. Okay, so control is significantly important. I think I just had given again the similar picture. I'm not going to repeat this again. So here we have this P converter and we have the power input and we have the power output. Here we have some load. And of course we are taking the reference signal and we have the control system and we are feeding back to this input of this P device again. So then by this way, we can give the control input, that is the error signal or reference signal. And we can give, we can control this power using this converter. Okay, so remember, high efficiency is important whenever we use the power electronic devices. The efficiency formula is eta is equal to P out divided by P in. Power output power divided by input power. That is the efficiency. So if I give 10 watts power at the output, how much power I am receiving? So if I receive again 10 watts at the output, then what is the efficiency here? So let us say according to this formula, this is the efficiency, right? Efficiency equal to power output, that is a 10 watts here, and then the power input is 10 watts. So I make the percent in terms of percentage, so multiplied by 100. So 10, so this is 1, so that is 100. So my efficiency is 100%. So that is how we calculate the efficiency. Power output divided by power input. Okay, and what is the power loss? Power loss is equal to power output power minus input power minus output power. So instead of having 10 watts at the output, I am getting now maybe 9 watts. So what is the energy loss here? So power input is 10 watts minus 9 watts. So this is input minus output. So my loss is 1 watt. My power loss is 1 watt. So you should remember these are very basic equations. I'm not really, I do not really need to talk about this in this part of the course, but I just would like to give you some reminder. Maybe you have already studied these things, these equations. I just would like to remind you because this is very useful when we talk about the electrical machines and how we are going to control. We are talking about the efficiency because we want to maintain the efficiency in the load side and during the transmission, power conversion, and so on. So this is our goal actually. So whatever the power we are giving at the input, and we want to get as maximum as possible at the output. We do not want to have loss. We want to reduce the loss as much as possible. Okay. So high efficiency leads to low power loss within converter, and smaller size, reliable operation. Efficiency is a good measure. Yes, that's correct. Totally correct. Efficiency is a good measure of converter performance. Okay, so now let's move to the next. So high efficiency converter. So we are giving power in and we are getting power out, and we use power electronic devices, power electronic based converters. A goal of current converter technology is to construct converters of smaller in size and weight, which process substantial power at high efficiency. So I have already showed you one small example, that is a fan regulator, right? We had seen just before. You can just relate that in this slide. So we have the power in, we have the power out, and we have to convert this power in an efficient way to deliver to the load according to the load requirement. So to study and understand power electronics, what are the devices available for design engineers? Maybe I got a job in one company as a power electronic design engineer. So what components I can use to design the power electronic circuits, to design the converter? So there are so many devices available, same like what you have studied in your analog electronics. We have resistors, we have capacitors, and we have inductors, right? RLC, RLC. These are the passive components, okay? And we have active components, which are transistors, operational amplifiers, and different types of transistors. For example, BJT, it's a transistor, FET is a transistor, MOSFET is a transistor. So we have so many different types of transistors. These all are semiconductor devices. So we have passive, we can use passive devices. We can use active devices to construct the power electronic circuit. Okay, there are several active and passive devices or components. We can also call that as a component. The both are same, or used to design power electronic circuits. In practical circuits, especially in power electronic side, we try to avoid inductors because of some magnetics effect. So we try to avoid these inductors to make the signal processing as efficient as possible. We also want to avoid resistors in our circuits, because a resistor is always making some voltage drop and consuming the energy, and it's dissipating the energy in terms of heat, and you need a heat sink and so on. Actually, we are talking about the high power applications now. So in the high power applications, you are going to have high voltage, high current. In that kind of situation, if you have this kind of resistors, the power dissipation will be very high, and the heat dissipation will be unwanted one in the application. So it will require the cooling fan and so on. So for this purpose, we are trying to avoid these resistors and these inductors. Sorry, not this one, inductors. So why we are avoiding these components? Because these are lossy components or lossy elements. So we try to avoid the lossy components when we design the circuit. So you are going to be an engineer. Maybe you get a job as a design engineer. You decide what component you want to use in your circuit. So again, a small recall: power loss in a switch, in ideal switch. Sorry, this is the wrong spelling. When the switch is closed, V of t is equal to 0, because when the switch is closed, the the current is flowing. So the voltage drop is 0. When the switch is open, it's an open circuit. So there is no current flow. It can stand any voltage potential. And in either event, either the switch is in a closed position or open position, V of t is equal to V of t multiplied by I of t. T equal to Vi. This is the standard formula you should remember always. So I just put with respect to time. So V of t times I of t. This is the formula, nothing special. So ideal switch consumes 0 power. So we want the switch to consume 0 power when the switch is in off condition. Okay, so the switching characteristics are important when we talk about semiconductor switches. Okay, the duty cycle we had already seen. Duty cycle means from on time to off time. That is the complete duty cycle. This is called the duty cycle. And this is called on time. This is only the on period of the pulse. This is on time, and this is off time. And this On time plus off time, that is called a duty cycle, one complete duty cycle. Of course, I had given some representations for this. So these all are some notations. The principle, the logic behind these notations are here it is. So on, off, duty cycle. So you can represent with any other letters. Okay. Of course, this T is the switching period. For example, now I call this as a TS, from on to off, one complete duty cycle. That is time period. What is the frequency formula? Frequency is equal to 1 by T, right? That is the formula you should remember, just like a P equal to VI. Similarly, this frequency F is equal to 1 by T. So that is what I had given here. That is the switching frequency, 1 by TS. Okay, DC component or the average value, there is also formula. Here we have to remember the formulas, differentiation formula, integration formula, and maybe you have studied about Laplace transforms and how can you analyze the circuit, because you should know the power across particular device, voltage across particular device, current is flowing through particular device, and so on. So in that kind of situations, we need to use some kind of circuit analysis. You have already taken the courses, I guess, network theory, circuit theory, and other courses. So I'm not going to repeat those things. So this is the standard formula for the average value. Adding low pass filter. Of course, you can also add some kind of LC low pass filter to remove some switching harmonics. Harmonics means what? This is the problem in the power electronics. Power electronics have a lot of advantages. It also have some drawbacks or disadvantages. One of the major disadvantages is harmonics. We will see harmonics in detail in the later part of the lecture, but harmonics means this is an unwanted signal which we are getting at the output side. So we need to use some kind of filter to remove these harmonics. And of course, when we talk about harmonics, then we have to talk about cutoff frequency. This cutoff frequency is important in any filter. So yeah, low pass filter, LPF, high pass filter, HPF, band pass filter, BPF, and band rejection filter or band reject filter. You remember the frequency response of these filters? Low pass filter means what? So we have the frequency response, it will be like this, right? So this is the output. So this, if you talk about this, so you are passing only the low frequencies and then you are blocking these high frequency components from the input signal. The high pass filter means what? It will only pass the high frequencies. So it will block all the low frequencies and it will pass only the high frequencies. This is the high pass filter. But of course, this is a ideal filter, but in practically it will not be like this. It will be a curve. There will be a linear curve. So here it will not be a sharp raising. It will be a linear raising, right? So this is LPF, HPF. So we can use, if you have some kind of impulses, high frequency impulses, then you can use this HPF or you can use this LPF to filter those impulse responses, and you can get the desired voltage or desired power to the load. So we are using different types of filters also in power electronics. So when we talk about the filters, then we have to talk about the cutoff frequency. For example, here for the low pass filter, this is the cutoff frequency. So it will transmit, it will transfer the frequency only up to this FC, and after that it will filter out. So these all are filter theory. I am not going to talk about this filter theory, but you just remember the cutoff frequency. When we talk about the filter, cutoff frequency is very important. And when we talk about the cutoff frequency, I think 1 by 2 pi RC, or is the standard cutoff frequency formula. Anyway, so we are not going to talk about these things, but we can use filter to filter out the harmonics. We will see the detail of harmonics in a while. Okay, this circuit is just a buck converter. And of course, we can add this control system to regulate the output voltage. And if this is the power electronic circuit, this is the power processing unit. And we also have the control system. And we have the load here. And we have the source here. This is the source. So this is this logic we have already discussed just before. So I'm not going to repeat again, but practically it will look like this if you look at from the circuit design point of view. So the control circuit, we will have the PWM, that is the pulse width modulator, and we have the compensator. And of course, we have this mixer that is going to compare the reference signal and your input signal to this unit. I am not talking about this since this is an introduction lecture. I think I have already given enough examples, but this is one more, another simple example. This is the laptop power supply system that you are using every day. So this is how the power system, the power supply system is working. So you are getting the power output from your outlet, that is stick contact. You are getting the AC voltage. And you have the charger, that is the PWM rectifier, lithium battery, and we are here. How many circuits we are having? You can see here. So we are having inverter. What the inverter is doing, and here we have the buck converter. What the buck converter is doing? DC to DC, right? DC to DC. So in the DC to DC converter, we have the buck. We have boost. We have buck boost. You can also stop me anytime. That's good. So AC to DC is a rectifier actually. Inverter is doing the opposite operation. It's going to be DC to AC. Yeah. This inverter is converting DC to AC. And we have, of course, the display backlighting, and we have the microprocessor and so on. So, but here we have the boost converter that is just going to boost the DC voltage. This is also DC to DC. So in just one a simple adapter, you can see how many different circuits we are using in the power supply system. And so that is what, like, it's really depending on the application where you are going to use. Maybe sometimes you will use only one type, or sometimes you will use the combination of different types of power electronic converter circuits. And similarly for electric vehicle power supply system. So nowadays almost we all are switching to electric car or electric bicycle. It's really convenient, and we are not using the gasoline, and we are not polluting the environment by emitting carbon. So we are using this, and in this electric vehicle power supply system, you should remember this is the entire system. So we have different types of converter circuits. So here also we have the inverter. Inverter means it's going to invert DC to AC. That's what I made a mistake just before. I said AC to DC. That's not inverter. So inverter is just doing only inverting DC into AC. And of course, we have different types of inverter circuits, and and we have the DC to DC converter also. Here you see, generally I mentioned about the DC to DC converter. I did not say buck or boost or buck boost. So it may be this is a buck boost combination. And we have the controller, and we have the microcontroller, and we have this electronic vehicles, automobile electronics. So depending upon the application where you are going to apply, so you will use the combination of different converter circuits. Okay, so power electronic incorporates concepts from the fields of analog circuits that I already told you, and electronic devices, and control systems, power systems, magnetics, that is the EMFT, electromagnetic field theory, and electrical machines, numerical simulation. So you will be using all these concepts in this course, power electronics. That is why this is an important course. You have to give importance from the beginning. Okay. So now numerical simulation. When I talk about the numerical simulation, I would like to remind you So please go through Simulink. This is one of the very beautiful and very practical software where you can model all these power electronic circuits. So PE circuits can be modeled using this Simulink software. And you can see, you can apply the input and you can see the output in the oscilloscope, digital oscilloscope. Of course, you can do the practical experiment and you can see the output in the real oscilloscope. And you can do modeling the same circuit in the Simulink software. And also you can see the output in the digital oscilloscope. Okay, but at least from the academic point of view, this is a really good tool for you to start with, Simulink and Simscape. So you can model even physical systems by using Simscape. It is just a little more advanced version of Simulink. So you decide which one you want to use. Yeah, I personally suggest MATLAB, and Simulink is part of the MATLAB. So it's free to use here, at least in the campus.